The last thing that we look at with exponents and logarithms is how do these equations apply to real life situations? What are the aspects that have exponential equations and logarithmic equations involved with them? And there's actually quite a few. So some of the things that exponential functions are used to look at. We've got population, compound interest. We've seen that already. We've done that formula a bit. Decibels we haven't. Richter scale, the pH scale from chemistry. We've also have some things that have exponential decay. Those are those exponential functions that are decreasing. So we have the half-life of radioactive substances and half-life of bacteria. We also have that when you take a medication or put a drug in your body slowly gets rid of that drug. It's not like that drug lasts forever. So if you have a headache, taking one Tylenol is not going to last you the rest of your life. It only lasts a certain amount of time. And your body uses it up or gets rid of it. So what is and how is that modeled? Usually by an exponential function. So the last section of this unit is looking at real life situations, the formulas involved, and then using your skills with exponential functions and logarithms to be able to solve them. And if you look back the last, 5 to 10 exams, provincial exams, I will say that one of the first 5 questions that uses a calculator is almost always a word problem involving exponential functions or logarithms. So what do we have to do to get ready for those? Well, first of all, formulas don't appear on your formula sheet. So here's our compound interest formula. We've seen this one before. If you got a question involving compound interest on your exam, they would give you the formula. Okay? Not guaranteed that the letters will be the same. They could choose whatever letters they wanted, but an explanation of each of those things will be there. A is the final value, P is the amount that you started with, your principal, N number of times compounded per year, R is the rate as the decimal, and T is time. So we have some questions that are relatively easy. Determine the final value of $500 after 10 years if it's invested at a rate of 2.5% and compounded monthly. So as far as working with this, we want to find the final amount, which is A. We know the principal or the initial amount is 500. So it's just a matter of plugging things into the formula. 1 plus the rate as a decimal divided by the number of compound periods. Compounded monthly means 12 times per year. And then 12 times 10. This is just seeing, do we have the skill to be able to put this into our calculator and figure out the value? Yes. Does this involve any solving whatsoever? No. Just type this in, push enter, and you get a value. So in 10 years, the investment would increase from $500 to $626.03. No logs, nothing with exponential needed to be done in this kind of question. So as far as, is this a typical exam question? Of course not, because this question could have been asked of you in grade 10. It's just, can you plug in the right numbers in the right spot and type them into your calculator? So here, again, I just want you to see, can you use the formula and type things into your calculator correctly? So read the question, look at the formula, try to plug things in yourself. All right, let's check how you did for plugging things in. Did you get all of the numbers right? Now I have the red brackets around the 2 times 5. Depending on your calculator, you might need to put that 2 times 5 in an extra set of brackets. On my calculator, when I do an exponent, it does little numbers, and I can write the 2 and the 5 in the exponent. But check it on your calculator. Check it on whatever scientific calculator you're going to use for the exam. You'll want to know, do I need extra brackets there or not? When I type this into my calculator, do I get that value? So often with calculators that have the little hat button, if you just did the hat of 2 times 5, this would only do an exponent of 2. Do that first, and then multiply your whole answer by 5. If you wanted this 2 times 5 to calculate, that's why you would need the extra set of brackets. Again, up till now, this is just using our calculator, not using anything new. When do we have to use the stuff that's new? Those are the questions that say, calculate the time. Why does this make a difference? Well, if we plug in everything that we know, how long would it take a $30 investment to double? So if I had $30 to begin with, when it doubles, the amount will be 60. 1 plus the interest rate is 0.07, compounded monthly divided by 12 to the power of 12t. So now we're solving for t in an exponent. How do we solve for things in an exponent? Well, we're going to have to use logarithms, and we have the one specific log law that lets you take an exponent out in front. That's why we have logarithms to solve this kind of equation. Now, whenever you have an equation like this with a number in front, okay, you could take the log of both sides to begin with, and it's not wrong. You have more log laws to do. But it does make sense to simplify first. How could I get rid of the 30 on that side? Because it's 30 times this. I could divide both sides by 30. Can you see if I divide both sides by 30, the other side just becomes 2. Oh, this is exciting math today. I really like the math that we're going to learn today. So just warning you, I'm going to have a lot of fun. So divide both sides by 30, and you get 2 equals 1 plus 0.07 divided by 12 to 12t. We're solving for t, and t is in the exponent. So we're going to need to use logarithms. We can take the log of both sides. Again, don't do too much at once. I'm just going to log of this side would equal log of this side. And now, because this exponent is to the entire thing inside of your logarithm, you have a log law that lets you bring that out in front. So I'd still have log of 2 on this side. That 12t could come out in front. And now, if I wanted to get t by itself, what's happening on the right side? It's 12 times t times log of 1 plus 0.07 divided by 12. Do you know that 12 is a number? Yes, good. Did you know that log of 1 plus, this is also a number? We don't know what it is, but it's equal to some number. So if I wanted to get t by itself and t is multiplied by a bunch of numbers, the opposite of multiplying is dividing. So if I divide both sides, I'm going to divide both sides by the 12 and the log 1 plus 0.07 divided by 12, I would get t all by itself. So I'm going to go to my calculator. Again, this is where you should practice things with your calculator. How does your calculator work to type this in? What are the things you need to do? So on my calculator here, I'm going to use the fraction button. Log of 2 divided by 12 log 1 plus 0.07 divided by 12. And I get 9.93 years. Oh, this is exciting. Time is always in years, so we need to make sure we have our units in our final answer. So if you were able to get, I'm going to view this entire thing. If you were able to get 7% interest, it would take about 10 years for $30 to double. Okay? Now, here's the crazy thing about compound interest. I'm going to redo this question, and we're not going to start with $30. We're going to start with $1,000. If I started with $1,000, for the double part, what would be on this side instead of 60? 2,000. Perfect. And then if we simplified the same way we did, what would we have to do to get rid of the 1,000 out in front? Divide by 1,000. And what would 2,000 divided by 1,000 be? 2. Can you see that in line 2, if I started with $1,000, it would be exactly the same. And it would take 10 years at 7% interest for $1,000 to double. In fact, compound interest always works this way. It doesn't matter how much money you have, okay? It would take the same amount for it to double. So if you can find a friend that is willing to give you $10 million, I mean, they're hard to find, I know, I've been trying for a while. If you can find a friend that's willing to give you $10 million and say, don't worry, I'll give it back to you in 10 years. And you found 7% interest in 10 years, it would have doubled. And you could give them back $10 million and you would have $10 million. Really exciting. Okay? If you can find a friend, if you walk the hallways, you might, not every day, but every once in a while, you might find a dime. 10 cents in the hallway. If you put that 10 cents into this account and waited for 10 years, you would have 20 cents. It would double. Now, that's not as exciting as $10 million, but it doesn't matter the amount of money. And what's really interesting, okay, I was about to say what's really interesting with compound interest, but that's like, sounds like a bad joke. But what's really fascinating with compound interest is that this idea of doubling can be simplified by something called the rule of 70, or sometimes it's called the rule of 72. If you take, it's a way to estimate number of years to double is always equal to, if you use the rule of 70, 70 divided by your interest rate. When we had 7%, what did we actually find how long it took to double? 9.9 years. Can you see if you put a 7 in here, what's 70 divided by 7? 10. It's a really good estimate. If you got 10% interest, it would only take 7 years to double. The reason why it's sometimes called the rule of 72 is because if the number divides nicer with 72, you use 72. If it divides nicer with 70, you use 70. So if you got 8% interest, what's 72 divided by 8? 9. So 8% would take about 9 years to double. Okay, if you got 6%, 72 divides nicer by 6, it's 12. So if you got 6%, it would take 12 years to double. Do you know what current interest rates are right now for most bank accounts? You're very lucky if you get 1%. Most of them are like 0.5%. So if you have $10 million, it'll only take 140 years to double. Oh. Banks aren't giving very good interest rates right now for making money. If you're a student and you have a student account, sometimes they entice you with a higher interest rate. Why do they give students higher interest rates? Because students don't have money, right? They're like, yeah, we'll let this person have their 10 cents double in 10 years. No problem, because they don't have very much money. But if you're older and you might have the possibility of having more money, as you get older, you have the possibility of having more debt, more likely. But as you get older, then those interest rates go down. Oh, there's so much fascinating math with interest rates and stuff. But this is just the rule of 70, 72. It's just a quick way to find out how long it's going to take your money to double. So if you get 5% interest, you could use this one. 70 divided by 5 is 14. It would take about 14 years for your investment to double. But this is just an estimate of the number of years it would take to double. Okay. Here's one for you to try. 4 years ago, Andrew invested in an RRSP. The interest rate was 5%, compounded quarterly. If it's now worth $2,500, how much did he originally invest? Okay, let's check how you did on those 3 questions. Here's the first one. So, the setup. We're solving for p. Is p in an exponent? No. No need to use logarithms. If I wanted to get p by itself, I could divide by this, type that all into my calculator all at once, and it would be $2,049.37. Okay, so we're not solving for a variable and exponent. We don't need to use our log laws. It's only if we're solving for something in an exponent that we do. So let's look at the next question. Calculate the time. So when we set up our equation here for $200 to get to $500, sure enough, what we're solving for, t time, is in the exponent. So we're going to need to use our log laws. Okay. So I'm going to do this in 2 different ways. The first way is if you decide to take the logarithm right away. If you decide to take the logarithm right away, you are not allowed to bring this 4t out in front, even though you would be tempted to, because the exponent of 4t is just to this part. Can you see that that exponent of 4t does not apply to the 200? I put a green dot between the 200 and that other part because it's multiplication right there. So what's our log law for multiplication? Multiplying inside of a log means that you can add. So I add log 200 plus, and now that exponent could come out in front. So I did that in 1 step. Once you've got the exponent out, it's just a matter of using your algebra skills to get t by itself. So I want to move the log 200 to the other side, so I'm going to subtract. Once I've subtracted, then I'm going to have to divide by the 4 and the log to get t by itself. Plug that into my calculator, and I get 30.66 years. So if you take the log right away, right? That's what I did in the first step. I took the log of both sides. And you have multiplication, then you have to use your log law that adds first before you can bring the exponent out in front. So you can see our skills in expanding logarithms comes into play when we're solving equations for exponents. All of those practice things that I said, expand completely, that was to help you with these questions. Okay? An alternative for this, which I'll do just off to the side in purple, is I would recommend dividing both sides by 200 first, and then taking the log of both sides. It will make it shorter. Everything else after that is almost exactly the same, except on this side, on the left side, you would get log of 500 divided by 200. I hope you can see that that's the same as this. And you just have less things to write because you've divided first. So if you can simplify your equation by dividing first, I highly recommend that. It makes your life a lot easier. Calculate at time it would take an investment to triple. It didn't tell you how much money. It doesn't matter what amounts you put in. You could do $10 and $30, $1 and $3, 1 cent and 3 cents, $1 million and $3 million. Because if you simplify by dividing both sides, you will get a 3 here every single time for when it triples. And just like for the amount of time it takes to double, it doesn't matter what amount of money you put in to begin with, it's going to take the same amount of time to triple. So that's where you want to find that friend that has $10 million. Because if you got 5% interest, it's going to take some time, right? You do your log laws of both sides, solve for t, 22 years, right? If you can find that person who's willing to give you $10 million, you say 22 years later, don't worry, I'll give you $10 million back and I'll take you out for coffee. It will have tripled and you'll have $20 million in the bank. Again, you let me know. We can go halves if you find someone willing to give us $10 million. I'll split half and half with you. We'll just invest it, make a lot of money, and then give it back to them with no interest. Next formula. Next formula looks at what happens, and this is fascinating. What happens if the compound interest formula, we could compound it monthly. Compounding it monthly is better than if it was compounded once a year. But then you say, well, instead of compounding it monthly, wouldn't it be even better if I compounded it daily? For sure. Because then every day the bank would pay you a little bit of interest. And the next day, you'd get a little bit of interest and make a little bit. Sorry, my voice, can't go high enough yet. But a tiny little bit on the interest you already made. And the next day you'd make a tiny bit on that interest and then a tiny bit on the interest from that day before. Whew. And so if it was compounded every day, you'd make interest on interest faster. Then you go, oh, what if the bank paid me every hour a tiny portion? And then the next hour, right? Like if you're getting like 5% interest and you invest $100, in an hour, they probably owe you a billionth of a cent. You're like, come on, pay up. Add that to my account. I want my account to have at least 15,000 decimal places, please. And they give you that billionth of a cent. You're like, oh yeah. And then the next hour, you make another billionth of a cent, and then you make a billionth of a cent, or whatever it is. But you're making money more often because you're getting paid every hour. And then you think, what about every minute? What about every second? What if they just paid me all the time? My bank account would just be, the numbers would just be increasing all the time. And if you changed it to all the time, this formula, your compound interest formula, the number E appears. That's that 2.718. It's really quite crazy the way that it does. In fact, do you want to play with your calculator a bit just to see where this comes from? So what's changing in here? This is a crazy idea, because what happens when n gets really, really big? If n is a billion, what does 1 over a billion get really close to? 0, right? If you have $1 and have to split it with a billion people, how much is each person going to get? Next to nothing. And the bigger that n gets, the closer this gets to 0. Does that make sense? So if n was really, 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 really big, the inside of the brackets should be really, really close to 1. Agreed? And if you do something really close to 1, here, let's mental math. I hope you're ready for this. What's 1 squared? Yeah, you're not ready. Yeah, okay, good. What's 1 cubed? 1 times 1 times 1. Still 1. 1 to the 100. I run out of fingers. Still 1, right? So looking at this, my gut says if n is really, really big, the inside's close to 1, 1 to any power is 1, this should be 1. So I go to my calculator. I go 1 plus 1 divided by, what's our big number that we want to start with? 1,000? Oh, I need brackets. To the power of 1,000. So my gut says this should be close to 1. Push enter, 2.71. Like, huh. What happens if I do a bigger number? So I'm going to $1 million. That sounds exciting. 1, 2, 3. Put in 1 million, 2.7182. As the numbers get bigger and bigger and bigger, it gets closer and closer to this number. This weird number like pi, just as eccentric and everything else that that number has. And so the formula, this part of the formula, 1 plus 1 over n to the n, that part just becomes e, and the interest rate part just becomes an exponent. And so now the question is, what would happen? Okay? What would happen if I had $2,000, 5% interest, and I could get paid my interest quarterly, which is every 3 months? Okay, this is our regular compound interest formula. We've done that already. There's the answer. If you did that for 10 years, your $2,000 would turn into $3,453.54. Now, if they paid you interest continuously, every millisecond or even more, your bank account would get added a little bit of money. And the next millisecond, you'd make a little bit of money, plus you'd make a little bit of money on that little bit of money. How big is this number going to be? Oh, we could play The Price is Right. So this is where, have you ever watched that show, Price is Right? Where they put up something like, what is the cost of this hole punch? And if you go over, you're out. But whoever's the closest but not over gets to go on to play the next game. So we're going to play The Price is Right here. What number is going to be in here? Do you think it, first of all, is everybody okay with the common sense idea that if you're getting paid interest more often, it will be bigger than this number? Good. So it's going to be bigger with that number. The question is, how much bigger? Okay? So, let's see here. How many people think that it's going to be more than $1 bigger? Everybody else thinks it's going to be less than $1 bigger? I picked a number that I expected everybody's hand to go up. See if you're paying attention. Okay? How many people think it's going to be more than $10 bigger? Okay? How about more than $100 bigger? Okay? More than $1,000 bigger? Okay? Because you're getting paid interest every millisecond. Okay? Are you ready for the answer? Yes? Question? Before it's like building anticipation, I know. It's a teaching technique to keep you engaged. Well, it's not the same because, like, if it's compounded quarterly, that means that in 3 months they give you $100. In the next 3 months, they give you another $100 plus they give you interest on the first $100 they gave you. And that's why this one's going to be more, because they're giving you little bits of money all the time, and you're also making new money on those little bits of money. So for example, in the first 3 months, on the right-hand side, you don't make any money. You just make your regular interest, the portion you would get. So at like 5.5% of 2,000, mental math, that's what, $110? 110 divided by 4 would be $27.50. $27.50 is how much you would get paid after the first 3 months here. Here, they would take that $110 and figure out, well, how many seconds are there in a year? Some huge number. They divide that $110 by that, how many seconds. They give you that amount of money right away. And now you have a new total that's bigger than $2,000. And you get interest on that. Okay? So here it is. Be prepared to be disappointed. Yeah, it's only about $13 more. Didn't I build it up like you should be like lots more? I was hoping I did that. It actually doesn't make a huge difference. And so when you have to borrow money, because it's going to happen sometime in your life, that you're going to have to go to a bank and borrow money, or go to a car dealership and borrow money. It's not so much how often they compound the interest. Most places do monthly. But the actual difference between monthly and daily isn't that much money. However, if you found out that your bank was continuously charging you interest, people would get angry. They'd feel like that wasn't fair, because it just feels not good. So banks will never say, yeah, we're compounding our interest continuously, because that extra $13 compared to the perception that people would have would be not worth it. So most places compound monthly. But the biggest thing when you have to borrow money that's going to make a difference, and we're going to look at examples of this, probably not today, but moving forward in our examples tomorrow, is the interest rate. If you can shave off 0.5% off the interest rate, if the person that's borrowing your money, you think, oh, they don't actually know that much math, if we take off a 0.5%, it's not a very big number, that could save you thousands and thousands of dollars. And we're going to look at that in some of our examples tomorrow. Terribly relevant and fascinating math that's coming up. So the amount, yes, the more often it's compounded, the greater it will be. However, that's not the biggest factor in how much interest you get or how much interest you have to pay. So it used to be that this formula, which I call the PERT formula, because it spells the word PERT, used to be that the PERT formula was on your formula sheet. So you would read a question and you'd have to recognize that if it said continuously, that you needed to use that PERT formula. Now they've taken the PERT formula off of your formula sheet, so if they wanted to give you this question, then they would have to give you the formula as well. So what's taken out from you that's really nice is you never have to guess which formula is it that I have to use, because they'll give you the formula in the question. Once you have that formula in the question, it's just a matter of plugging things in. Here it's asking for what's the interest rate. Well, the R is in the exponent. I'm just going to solve this one, not even look at the stuff I wrote before. I would recommend, since we're multiplying here, as a first step, divide both sides by 200. R times 3 is the same as 3R. Ooh, if you erase behind, does it go away? Yes, it does. There we go. And then, because it has an e as a base, you could take the regular log of both sides. That's perfectly fine. However, if you take the natural log of both sides, this 3R could come out in front. And then the natural log of e is equal to what? This is mental math. What's the base of a natural log? Base of natural log is e. What do logs solve for? They solve for exponents. So e to what exponent would be e? 1. Natural log of e would be 1. And so this side just becomes 3R. And to get R by itself, just have to divide both sides by 3. Go to your calculator. Rounded to 3 decimal places, 0.054. So your interest rate would be about 5.4%. This question is more or less the same. I'm going to leave this one for you to do on your own. I'll put up the video so you can check your answer later if you want to check the video, the answer, or if you just want to write down that the answer is 9.049 years. So when you're checking it on your own later, you're fine. And we'll move on to population. So another use of the PERT formula is to model population. Most populations, when they get big enough, can be thought of growing continuously. In fact, during this sentence that I just said, somewhere in the world, somebody was born. Probably more than one person was born. If I keep talking, more and more people are born. If I shut up, they still get born. I can't help it. At the same time, people are dying, right? People are being born and people are dying. Well, it's not continuously, but there's not like there's not a website that says this is the exact human population, and you can watch it go up. Oh, it went down. Up, went down. Oh, there's a big earthquake. It went down a bunch, and then, right? Then I don't know what happened in that country, but 9 months after New Year's, and all of a sudden, boom. We've got a whole bunch of babies being born. I'm not sure, okay? But we can't say exactly what the population is. It's so close to growing continuously that we often model population as continuous growth. And it's with that same PERT formula that we can do it. We look at the rate that it's changing, and we have an initial population and final population after T years. So 1981, population Vancouver, 1.38 million. What will it be in 2011? Well, if we put 1.38 million as our first amount, our rate at 1.7%, 2011 is 30 years later. It's just a matter of typing that into your calculator and finding the number. So part B, when will the population be 6 million? So again, we set up our equation with everything we know. I changed my 1.38 to millions. Does that make sense? Instead of writing 138,000,000, I wrote 1.38 million and 6 million. I basically divided both sides by a million just to have smaller numbers. I'm going to see if I'm happy with what I did next. Yes, I'm very happy. Whenever you have that number in front, you could take the log right away, but it's going to be easier for you if you divide. It simplifies. If you can get, in other words, your power by itself, your log laws are easier. So I divided both sides by 1.38 just to get my power by itself. Since the base is e, and I'm solving for an exponent, I have to take the log of both sides, but it makes sense to take the natural log of both sides. And my log law says that I could bring that exponent out in front. That leaves natural log of e all by itself, and natural log of e is equal to 1. Now, if you didn't remember that natural log of e was equal to 1, then when you go to divide, can you see that you would also divide by the natural log of e? Which, whether that's there or not there, doesn't change your answer because it's equal to 1. So solving for t comes up as 86.5 years. And since the initial population was in 1981, if we add 86.5 years after 1981, it looks like somewhere in the year 2067, Vancouver is going to be at 6 million. Okay? Why is this helpful? Well, if you're a city planner for the city of Vancouver, what kind of problems are we going to have in 20 or 30 years if the population is growing at this rate? What kind of things do we have to do to our infrastructure to change that? So we can use these population models to help us get ready for the future. And if you can get ready early enough, you can avoid problems. And so this is where mathematics can help us predict what could happen. Not guaranteed to happen, but a prediction of what could happen. Okay, and the last questions that I like to solve with populations. It's with animals. Population of a herd of gophers was first studied. It was 15,000. 6 years later, it was 18,000. If the population grows continuously, so this continuously part tells you that it's the PERT formula. That's in the old curriculum. It would have been that way. Now they would give you that formula. Using the formula PERT, A equals PERT, or whatever letters they choose to use. Okay, how long would it take to triple? So we want to find t, okay? And if you put in a number, I've got it here, 15,000, 45,000 e, we don't know r. You see the problem? We want to find t, but nowhere does it tell us what r is. And if you have two variables in a question that you want to solve, you won't be able to solve it. So if we try to solve this directly by using 15,000 and tripling it to get to 45,000, we don't know r and we don't know t. We want to find t, but before we can find t, we need to find r first. Do we have enough information to write an equation where the only thing we don't know is r? Well, we have an initial population of 15,000. We know that in 6 years, it's 18,000. Can you see that I can make an equation with that? 15,000 originally, 18,000 times 6 years. That makes an equation where the only thing I don't know is r. Where's r? R is in the exponent. I'm going to need to use my logarithms. I'm going to divide by 15,000 first. Simplify, that gives me 8 over 15. Then I can take the natural log of both sides. Natural log of e is 1, divide both sides by 6. And here, if I go to my calculator and I type it in, don't worry, I'll let you see it again. Natural log of 18 divided by 15, all divided by 3. Was it divided by 3? Divided by 6. All divided by 6. I get 0.03038. I might just store this into my memory as x right now. Or if you really, because it's the letter r, you can actually go, I'm going to store it as a letter r, if you wanted to. Because now that we know r, we can go to this side and now find t. Now, the question that students always ask me, they say, does it matter? Should I use the 15,000 and triple it to get 45,000? Or should I use the 18,000 and triple it to get 54,000? Does it matter? Will I get a different answer if I use one number or the other? No. Remember, just like with money, how I said it doesn't matter how much you had originally. It's going to take the same amount of time to double or the same amount of time to triple. This is the same thing here, because if you divide both sides by 15,000, okay, if I use 15,000, divide both sides by 15,000, I get 3. If I had 18,000 and tripled 18,000 to 54,000, when I divide by 18,000, I'd get 3. It'd be the same either way. In the brackets here, I've got the 0.03. Do you notice how I put dot, 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 dot? It means I'm keeping all of my decimal places until the very end. Again, t is an exponent. Take the log of both sides. After taking the log of both sides, you can divide. Now, in this case, right, natural log of 3 divided by 0.03. On my calculator, I could have just done natural log of 3 divided by second answer, because my answer was still stored there to get 36. But I stored it as r, so I could have also done natural log of 3 divided by r and got the same answer. Now, there's one tiny little mistake in this question in the actual wording of the question itself. Anybody see the tiny little mistake? Anybody want to guess? A group of gophers isn't called a herd. That's right. I did that on purpose. Do you know what a group of gophers is called? This is something about the English language. For every animal, we have a different word when the group of them get together. So gophers, which are like little annoying squirrel-like thingies, okay, they're called a colony of gophers. Right? Herd we use for cattle. Cows, a herd of cattle. Okay? Herd of goats. Goats and cattle have that. What about fish? Don't have a herd of fish? We say a school of fish. In fact, we make up the most obscure words possible. So this next one is actually correct. This is one I'm going to get you to do on your own. A group of rhinos, perfect timing, is called a crash of rhinos. I don't know why. So while you're working on this one, I will find out some names for you of different animals. There's some really interesting ones. Crows. Crows are blackbirds. Do you know what you call a group of crows? A murder of crows. Crazy English language. So I'll find out, and you can ask any animal you like, but if you have a group of rhinos, it's called a crash of rhinos. I would recommend not running into a group of rhinos. Ooh. A coalition of cheetahs. That's a good one. Oh, maybe you know this one. Dolphins. A pod. Okay. Gnu's. First of all, that's a crazy word. An implausibility of gnu's. Who'd have guessed? Leopards. You know what you call a group of leopards? A leap of leopards. Like, who made this up? Like, this must have been a guy, like, just joking around. It's like, you got, all of a sudden one day they decided that one person was going to make crazy names. And you're like, oh, there's a bunch of mice together. We'll call them a mischief of mice. Are there any that you are interested in knowing? Any animals? Like a prickle of porcupines? Because I've got just about every animal name here. Some of them have more than one. So zebras, you could just go with the classic herd of zebras. If you wanted to add a little bit, you could call them a zeal of zebras. An annoyance of teachers. Just kidding. So I put an answer up here so you can check it later. You should have got R to be 0.02 with a bunch more decimal places. And then when you solve for t, you would get 28.56 years.